If the bonds holding your DNA together were too strong, your cells could never pull them apart to read your genetic code. If they were too weak, the double helix would simply fall apart at body temperature. To understand how life balances on this exact chemical knife edge, we are going to build the forces of molecular biology from the ground up, giving you the tools to master competitive exam chemistry along the way. All chemical bonding comes down to a single drive: atoms using electrostatic attraction to reach their lowest energy, most stable state. We often learn that bonding is a simple choice. Metals and nonmetals form ionic bonds, while nonmetals sharing electrons form covalent bonds. The reality is measured by electronegativity, which is an atom's physical pull on shared electrons in a tug-of-war. Looking at this numerical spectrum, we can see the exact mathematical thresholds. If the difference in electronegativity between two atoms is 0.4 or less, they share electrons equally in a nonpolar covalent bond. A difference between 0.5 and 1.7 creates an uneven polar covalent bond. Push past 1.7 and one atom completely strips the electron away, forming an ionic bond. Bonding exists on a fluid spectrum. The category we assign to a bond depends entirely on how aggressively one atom takes electrons from another to achieve stability. To measure the strength of covalent bonds, we look at bond dissociation energy. This is the precise amount of energy required to break 1 mole of bonds in a gas phase. You have to put energy into a system to break a chemical bond. It requires an active input of work. This data table compares the energy requirements for different carbon bonds. A single carbon-carbon bond requires 347 kilojoules per mole to break. A double bond increases that requirement to 614 kilojoules per mole. Higher bond energy means higher molecular stability. Moving from bond strength to molecular shape, let's examine this 3D model of a water molecule using VSEPR theory. The two unshared lone pairs of electrons on the oxygen atom strongly repel each other and the bonded hydrogen atoms, physically forcing the molecule into this specific bent geometry. Because of this bent shape, the highly electronegative oxygen pulls electron density away from the hydrogens, creating a partial negative charge at the top and partial positive charges at the bottom. When a second water molecule approaches, these opposite partial charges lock together, forming a moderate-strength hydrogen bond. A molecule's geometry directly dictates its overall polarity. That polarity is the necessary prerequisite for the intermolecular forces that allow discrete molecules to condense into complex liquids and solid structures. Even symmetrical, nonpolar molecules experience London dispersion forces, the weakest but most universal force. In atom B, randomly moving electrons can concentrate on one side momentarily. This creates an excess of electrons, resulting in a temporary partial negative charge. This diagram shows what happens next. The temporary negative charge on atom B repels the electrons in neighboring atom A. This creates an induced dipole, and those dotted lines represent the resulting fleeting electrostatic attraction holding the two atoms together. These two molecules share the same chemical formula but have different shapes, illustrating polarizability. The linear N-pentane has more surface area for temporary dipoles to interact than the spherical neopentane, creating stronger dispersion forces and a higher boiling point. Take a moment to test your active recall. Calculate the electronegativity difference between carbon at 2.5 and oxygen at 3.5. Determine the bond type and compare its breaking energy to a carbon-oxygen double bond. A difference of 1.0 makes it a polar covalent bond, and breaking it requires less energy than breaking the double bond. While individual London dispersion forces are incredibly weak, they compound exponentially across large surface areas, generating enough collective force to hold massive nonpolar structures together. When we zoom out to the scale of biological macromolecules, we see all three of these chemical forces operating simultaneously to construct the machinery of life. In this model of a protein chain, The thick red backbone represents the strong primary covalent bonds. These require massive energy to break and serve as the permanent structural skeleton of the molecule. Next, we add the moderate intermolecular forces. These blue linkages represent hydrogen bonds acting like molecular origami. They pull the rigid covalent backbone into specific, reversible folded shapes, like an alpha helix. Finally, we see the bulky side chains in yellow clustering together in the center. Their individual London dispersion forces compound, driving these non-polar carbon chains away from water and tightly packing them into a stable hydrophobic core. This summary matrix categorizes the entire hierarchy. Covalent bonds dictate primary sequence stability in the hundreds of kilojoules per mole. Hydrogen bonds, at roughly a tenth of that strength, handle secondary folding. Dispersion forces, the weakest of all, handled the final 3D packing. In biology, a molecule's shape determines its function. By mastering the energetic hierarchy of these chemical bonds, you hold the exact blueprint for how atoms assemble into the architecture of living things.